Thanks for joining with me to listen on the second chapter on our course in solid state physics, and the name of our second chapter is Bonding in Solids. So what we have to cover in this second chapter is that we have 6 different subchapters, and I will first in this lecture start with the very basics. So I will provide you a motivation, what this chapter is about and why we will uncover it, and then I will go through the first subchapter, so 2.1, attractive and repulsive forces. So I will start by just telling you that what we want to do in this chapter is that we want to introduce the different mechanisms that are out there that then give rise to formation of solids. Of course, in principle, the same forces would give rise to the formation of liquids and other substances, but basically here our focus on this course is in solid state physics and solid state matter, so we are only interested in solid form. And we're here interested to understand the mechanisms that then give rise to this bond formation that then gives rise to a formation of solids. So what are the forces and what kind of bonding exists between atoms when we are making a solid? And what happens subsequently, that when bonding occurs, we have a formation of crystals, so periodic structures, and in addition, of course, we will have formation of other structures that have order but may not be as periodic as crystals. So for example, sugar and salt are good examples of the substances that we are covering here. So if you look at of those white powders, sugar and salt, and if you would look carefully enough and with a high magnification enough, you would see that in fact they are small crystalline flakes that are giving rise to these substances. Incidentally, regarding X-ray diffraction, like a snowflakes, that's also an example of a crystalline substance. And on a crispy, cold winter's day in Scandinavia, when sun is shining and you are looking at the surface of a snow, you see it glimmering quite strongly. And then depending on the kind of orientation the flake is, the glimmering makes the surface shine. So that resembles me of a powder X-ray diffraction, and saying sugar and salt here and saying powder made me think of other things that comes to mind out of powders. I'm that kind of guy. So when somebody says powder, I'm thinking of X-ray diffraction and snow on winter's day, cold winter's day. Other examples, I'm always branching out. Sorry about me, but I hope you don't mind too much. Another example, and there was a Nobel Prize on the discoverers. DNA molecules, they are also highly structured, but not periodic in the sense that we understand when we are saying we have a crystal. Another substance, a family of proteins from biology, are collagen proteins. And you may not heard of these, but these are actually quite abundant and quite important proteins in mammalian organisms. So 30% of the weight of mammalian protein mass comes from these collagen proteins. So there are around 30 different collagen proteins, and they give rise to much of the kind of structures that we have in our human body, for example. The kind of skin, there's a lot of collagen in there, and like the extracellular matrix that surrounds cells and protects our different organs in a way, like there's also collagen involved and so forth. So this is actually very important. DNA, for whatever reason, is maybe more known of a biological molecule or protein that we think that are important, but it's not the only one. Not at all. Another example is diamond. I'm a fan of diamond not because they're so shiny and expensive, but because it has a so peculiar and unique properties in terms of its thermal conductivity and so forth. It's also highly useful in engineering sciences, so I really like diamond. This is the structure, the diamond lattice, and please note that the red spheres and the blue spheres, depending on the lattice, they either may be identical lattice points or they may be different. But in practice, when we make, for example, a diamond structure, we have just carbon atoms. So we should replace those blue atoms with red spheres, and that's it. So these are the things that we will be covering. And we want to understand how these kind of what are the forces, what are the principles, the governing principles that give rise to this kind of formation of different substances. And as you can see on this list, there's a whole range of different kinds of substances. And we appreciate the fact that they do look microscopically quite different, but nevertheless, there are relatively simple rules that dictate how these structures are being formed. So I think it's very, very interesting that in physics and in the universe, these kind of hierarchical structures seem to emerge out of relatively simple recipes, like relatively simple forces. But let's get forward. I don't want to stop here. We have, as we know from high school chemistry, that there are these kind of idealized limiting cases of different types of bonding forces and subsequently solids. So one ideal case is that we consider ionic bonding, and there a prime example is sodium chloride. That's a classical example that we have salt, and that's a classic example of ionic solid. On the other hand, we also may have covalent bonds, and their examples are, for example, the numerous carbon allotropes, graphite, graphene, diamond, carbon nanotubes, fullerenes, and so forth. That's a very good example. If you're more into engineering sciences, of course, silicon as a semiconductor is another example of a covalent solid. Germanium and CG alloys, that if you're not interested in carbonous materials. Metallic bonding, and in a way, this is a kind of more general case of a covalent bonds, but usually we say that's a different kind of bonds because the macroscopic properties of metals are quite different from covalent solids. Because of this difference, usually we distinguish between covalent solids and metallic solids. And finally, what we will cover in this chapter is that we go through van der Waals forces and van der Waals bonding, and their examples are, for example, DNA and solids formed out of noble gases, so-called van der Waals crystals. And they solidify only at very cold temperatures, so in real life, we don't really see van der Waals crystals forming. But if you go to a few kelvins, yes, we start seeing noble gases to form solids. What happens in terms of the physics and chemistry here is that only the valence electrons participate in formation of bonds. And valence electrons, they are the outermost electrons that an atom has. So please remember this. This is basically what happens, and the only electrons we need to consider when we are thinking of bond formation. So the inner shell electrons, and those are called core electrons, they are very tightly bound to the nuclei so that they don't much participate in formation of solids. So that's the kind of rule of thumb that maybe is a good thing to remember for the future. And now that I have gone through the introduction of this chapter, I will go to the first part. So I will very briefly cover the different forces, the attractive and repulsive forces, and superficially explain to you what are the origins of those forces. So we are looking at stable compounds. So we are looking at a piece of a crystalline solid, and that remains to be in a crystalline form, so it's stable. So we're not interested in solids that they then remain in their form. And this means that the molecular or the crystalline structures that we are looking into, they are in equilibrium. So that somehow there's a balance that has been formed, and energy-wise, for example, energy has been minimized, and the system is in equilibrium and doesn't spontaneously change its phase. And what this means that we have this kind of equilibrium in place in the system is that we need both repulsive forces and attractive forces between the atoms so that they form a stable compound. So if there wouldn't be attractive forces, there would not be any mechanism that would give rise to a solid. And if there would not be repulsive forces, then at some point the atoms, they would just come together endlessly and they would form a black hole or something. Like there also must be some repulsive forces that kind of keeps the atoms as atoms, and they don't like the electrons don't kind of are not being sucked into the nuclei, and nearby atoms are not being forming new elements, so that they remain as atoms. How do we do things in practice? Is that we want to be able to write a Hamiltonian that then describes how an electron is behaving or how an atom is behaving inside the nuclei. And how do we do that in practice then is that the forces that we want to place into this Hamiltonian that is describing the quantum mechanics is that we want to transform the forces into potentials. Because potential is something we can directly then place and then we can solve or try to solve our Hamiltonian. And here a commonly used potential form this is just a generic form of a potential, is that we have phi potential, and it's of the form that we have some kind of constant A divided by R to the power of N minus another constant B divided by R to the power of M. And R is the distance between the atoms, and we want to have a potential trap, so that we want to have a stable potential and stable substance. So N must be greater than M, so that the repulsion prevails at short enough distances R. And when we have this form, there will be some kind of equilibrium position situation where the atoms form a solid equilibrium substance. And this above equation for the potential, it's also known as the interatomic potential because it's a potential and it's describing potential between two atoms. It's a very generic form, but it's the simplest that we can muster, and this simplest form for a potential that we can imagine already provides us with the kind of most important ingredients to understand bond formation. So we are pretty happy with this simple potential. The question then might be that how do we turn this potential into a force? And the question earlier was that what do we do? How do we describe these forces in quantum mechanics? And there the answer was that we use potentials. And now we want to understand the kind of bond formation in macroscopic picture. So we want to understand how a potential is turned into a force. And we have this potential of the form that we just discovered. And then we know that we are in a static situation. So we are in an equilibrium situation, so that there's no kind of moving of currents around, so that the atoms don't move quickly away from each other. The electrons do not move around too much. And what this implies that we have electrostatic approximation in hold. So we don't need to. We're only interested in static electric fields. And then, because we are only interested in static electric fields, we know that this electrostatic electric field is then entirely defined as a gradient of a potential field phi. So recall this from electrostatics, so that the electric field vector quantity can be under the electrostatic approximation, written as a minus of nabla over the phi potential field. And this, when we combine that with the Lorentz force equation, gives us a means to relate force with the gradient. So recall Lorentz force F equals Q, the charge of the particle, times E, the electric field, plus the charge of the particle Q times the velocity of the charged particle, and cross product with the magnetic field. And now we are just assuming that we don't have external magnetic fields in place. or they are just weak enough that we can neglect them, and then we're left with the F equals QE. And now we just replace the gradient notation for the E, and we see that the force is proportional to minus Q times the gradient of a potential. And this is the case, that is okay, this is valid when electrostatic approximation holds. And that holds when we have a static situation, so that the atoms are in place, they don't quickly move around, so we are not studying plasma, we're studying a solid substance, so that the electrons, they don't move around much, and the atoms don't move around much. And then the rest is direct consequence of these assumptions. So now we have a potential, and now we can try to understand things by just looking at the potential. And this is what the figure tries to show you, how things look in practice. So we have an attractive part, so we have attraction, and we can see this attraction to be due to the electrostatic forces. So like we may have, for example, a positive ion, and we have a negative electron, and then they are like attracted via electrostatic forces. And then we also have repulsive forces, which arise at short distances due to the Pauli exclusion principle. So for example, we have two electrons, and they are fermions, and they cannot be in the same quantum mechanical state. So then that's what then happens. And I was wondering some time ago, and I was very pleased that one student was also wondering a while ago, that my high school teacher told to me that there's only 4 fundamental forces on universe. So gravity, weak force, strong force, and the electromagnetic force. And then I'm here happily saying to you that there's also a 5th force, because repulsion is somehow created because of Pauli exclusion principle. And that seems to be very contradictory. So what is this 5th force that we have just discovered? And here what I think myself is that we should be very careful when we are saying that there are 4 fundamental forces. Maybe a better description would be that we have 4 fundamental interactions, and those are the interactions that govern what happens in the universe. And now what we are doing with the electrons is that we are describing electrons using a Hamiltonian, and what we put into the Hamiltonian is that we let these 2 electrons to interact via electromagnetic interaction. And because of this electromagnetic interaction, and due to the fact that the electrons are fermions, Pauli exclusion principle pops out. And then that's why we have repulsion. So fundamentally, I would say that this repulsion force is also of electromagnetic origin in a way, but it's more complicated, because in fact it arises from the fact that the electrons are fermions, and they cannot be in the same quantum mechanical state, in the same quantum mechanical system, and this manifests itself in the Pauli exclusion principle, and this is the kind of what gives rise to repulsion forces. But maybe this helps, or I'm sorry if this confuses you, but at least we kind of know and can contend that it's not gravity in place, it's not strong force, weak force, but I would still rather say that this is electrodynamics taking place. But just we now need to also include the fact that we are dealing with fermionic particles here. So fermionic wave functions, they are anti-symmetric. And you know that I like symmetry, and this is also just another case of a symmetries in the universe, so that they this is cool piece of physics. So these are the kind of basic things that we need to understand how bond formation happens. So we want to find a description of a potential, and when we have a potential, we have a function like this guy here, and it may consist of different parts. It may have attractive part, but in addition to just attraction, we also need some repulsive part, and this arises from the Pauli exclusion principle, so that the fermions want to be in the same quantum state, and then we have this total potential form. And then we calculate the gradient of this potential, and we take the minus of that, and then we see that we have forces in place, and those forces give rise to the equilibrium position we know as a solid. So this is the approach we will kind of continue next, and we will go through the different types of solids that are being formed based on different types of bonding processes. But thanks for listening, and please let's quickly follow to the second chapter in our course. Thanks and bye-bye.